Is my screen visible? Madhavan and Krishnakant, is my screen visible?
Yes.
Yes, ma'am.
Yeah, screen
Okay.
visible. Yeah.
Okay, okay.
Blank screen is visible.
Okay, sir. Okay.
Yes, sir.
Krishnakant, which class you are in?
9.
Ninth standard. Okay, fine. Fine. How about Madhavan?
Yes.
Madhavan?
12th completed, ma'am.
Okay, I've done with your 12th. And are you doing repeater or, are you repeater or something?
No, ma'am. First year.
First year of what?
Neet.
Neat.
Acha, first year it means you already completed 12th.
Yes, ma'am.
Oh, acha, repeater. It means repeater. Okay.
Fine. So actually, we have started with electrochemistry, which is the chapter in 12th standard. So
Yes.
already we have done with 2 classes. And if you want to check what are all the topics we have discussed in last few classes, please check for the videos in our YouTube channel so you can cope up with the class. Okay. But today, to start with, please listen to the class. If you have any doubt or if you have any difficulty, please let me know. It is going to be the continuation of our previous classes. And if you're in 9th standard, also no problem, Krishnakant. You just listen to the class. That's enough.
Okay, ma'am.
Fine. Fine. Good evening, Marimuthu.
Good evening, ma'am.
Kartiga, no?
Yes.
Good evening, ma'am.
Okay, so fine. We'll start with the class. So last class we have been discussing electrochemistry, and in which we have discussed the working principle of Daniel cell and how to represent a cell, and also we have discussed how to write the overall cell reaction and all that. After which we have discussed the very important topic, which is physical significance of electrode potential. Based on the electrode potential values, you can predict which is anode, which is cathode, in which metal oxidation occurs and which metal reduction occurs, which metal will be highly reactive, which will be the best oxidizing and reducing agent, and all that. And after which we have discussed Nernst equation also. Could you please tell me what is Nernst equation and its biggest application? What is Nernst equation? So basically, electrode potentials are the values which we have in standard state, right? What is the standard condition? If you dip a metal in its own electrolytic solution, then we can expect oxidation reaction or reduction reaction. If any reaction occurs, either it can be oxidation or reduction, there will be a potential developed between electrode and electrolytic solution, and that potential is called electrode potential, right? And if the potential is developed because of oxidation, that is called oxidation potential. If the potential is developed because of reduction, then that is called reduction potential. And among which conventionally we'll be using only reduction potential, right? And those datas we have in standard condition. Standard condition is nothing but the electrolytic solution. What I'm talking about is a 1 molar concentration, 25 degrees Celsius, and pressure is 1 atmospheric pressure. If you measure the electrode potential under these conditions, then that potential is called standard electrode potential. And for all the elements, we have standard electrode potential. Standard electrode potential, which is called EMF series, but basically that is for standard condition only, as I've told you. For other concentrations other than 1 molar concentration, we couldn't use those values, but we can of course calculate the values. So to calculate the electrode potential of electrode potential for other concentrations other than 1 molar concentration, then we can use Nernst equation. Fine. So we have discussed the Nernst equation for electrode and cell as well. Could you please tell me the Nernst equation for electrode? Nernst equation for electrode. How to represent the potential? Basically, capital E represents potential, and if it is E naught, then that is the potential of electrode in standard condition. If it is E naught cell, then this is the standard cell potential. Okay, fine. If it is just capital E, then this is the electrode potential at non-standard condition. And if it is E cell, then this is the cell potential at non-standard condition. Non-standard condition is nothing but the concentration of electrolytic solution is not 1 molarity. Fine. So Nernst equation is helpful in finding the values of electrode potential and cell potential at non-standard condition. And basically the formula was E is equal to E naught minus 0.0591 divided by N log 1 by concentration of metal ion, right? What is N? See, last class we have discussed this equation and we have done one problem also. What is this N? N represents number of electrons involved, right? And similarly, E cell is equal to E naught cell minus 0.0591 divided by N log concentration of product divided by concentration of reactant, right? And there is a formula to calculate E naught cell, right? What is the formula? Formula to calculate E naught cell. This also we have discussed under physical significance of electrode potential. E naught cathode minus E naught anode. Fine. And also from the sign of E naught cell, we can predict whether the given reaction is a feasible one or not feasible. If the sign of E naught cell is positive, then the reaction is a feasible reaction, or it is also called as spontaneous reaction. Similarly, if it is negative, then it is non-spontaneous reaction, the chemical reaction which cannot occur by itself. We can predict the feasibility of the reaction from the sign of E naught cell, or we can use the sign of delta G naught as well, right? What should be the sign of delta G naught for spontaneous reaction? It is just the opposite of, very good, it is negative. And for non-spontaneous reaction, delta G has to be positive. And there was a relationship between delta G naught and E naught cell. Do you remember that? There is a relationship between delta G naught and E naught cell. Delta G naught is equal to minus N F E naught cell. Here N is the number of electrons involved. And what is F? We have discussed about F also. F. It is 1 farad. And what is the value of 1 farad?
96,500 no to the power minus 1.
Very good. 96,500. It is basically the charge of 1 mole of electron. Since it is the charge, unit has to be coulomb, and it is the charge of 1 mole of electron, it is per mole. So 96,500 coulomb per mole is the value of 1 farad. Fine. So under this Nernst equation, we have discussed one problem also. This will be our next problem here. This is the cell representation, and what this double vertical line represents? What this double vertical line represents? In a cell representation, double vertical line represents the salt bridge, and left side we'll be having anode, and right side we'll be having cathode. Could you please tell me what reaction will occur in anode? What reaction we can expect in anode? Is it reduction or oxidation?
Oxidation reaction.
Oxidation. And of course in cathode, reduction reaction. Here we have two kind of species. One is iron, another one is hydrogen. Could you please tell me which species will undergo oxidation? Which will undergo oxidation? Which is the left side to the salt bridge? I've written the anode cathode.
Fe2 plus.
So iron will get oxidized and hydrogen will get reduced, right? So actually, this is the question. Could you please read this question?
Write the Nernst equation and EMF for of the following cells at 298 Kelvin.
Okay, so they're asking us to write the Nernst equation. This is question number 1. And they're asking us to find the EMF of the following cell. EMF is nothing but the cell potential. And could you please tell me whether this cell is under standard condition or not? A standard condition means both the electrolytic solutions concentration has to be 1 molarity. Here, the concentration of Fe2 plus was 0.001 and the concentration of H plus is 1 molarity. So, is it under standard condition? If the no, because the concentration of Fe2 plus is not 1 molarity. So, this is under non-standard condition. So, definitely we have to calculate E cell. It is not E naught cell. Fine. And we know we can use the Nernst equation to find EMF of the cell, right? So what is the formula? Since it is cell, the formula is E cell is equal to E naught cell minus 0.0591 divided by N log concentration of product divided by reactant. So we have to find the number of electrons involved. We have to find the concentrations of product and the reactants. And finally, we have to find the E naught cell also. So first of all, to find the concentration of product, reactant, and number of electrons involved, we have to write the oxidation, reduction, and overall cell reaction. So first, let us start with anode reaction. Anode reaction is nothing but the oxidation. So here, the species which will undergo oxidation is iron. So here we have two chemical species under anode. One is Fe and another one is Fe2 plus. So if the what is oxidation? Basically, chemical species will lose its electron. So we have to start with Fe, and if this ion has to get converted into Fe2 plus, then how many electrons should Fe have to lose? How many electrons have to lose?
2 electrons.
Very good, 2 electrons. So very good, Kana. 2 electrons have to be lost by anode, which means ion. And how about cathode? In cathode, we can expect a reduction reaction. Reduction is basically gain of electron. Here we have two chemical species. One is H plus and another one is H2. So the process has to be H plus has to get converted into H2. So H plus have to get converted into H2. So first of all, we have to balance this equation. Left side we have only one hydrogen and right side we have two hydrogens. So we have to make it as 2H plus. So how many electrons has to be gained by H plus to get converted into H2?
2 electrons.
Very good. Because here one is H plus and another one is also H plus. What is H2? Two hydrogens has to make a chemical bond using 2 electrons. So here this got no electron, this also got no electron. So each species should have 2 electrons. Each species should have 1 electron each. So basically totally we should have 2 electrons. So 2 times of H plus has to gain 2 electrons to get converted into hydrogen. So here they have given the physical state of iron as solid. The physical state of Fe2 plus, of course, it will be in liquid or an aqueous medium, right? All the ions will be in aqueous medium. And here also, H plus will be in aqueous medium. And what will be the physical state of hydrogen?
Gaseous state.
Very good. It is gaseous state. So this is the anode reaction. This is the cathode reaction. And we have to add both the reactions to find the overall cell reaction. So to add the reaction, we have to match the left side of the first reaction with right side of the second reaction. Nothing is matching here. And also we have to match the right side of the first equation and left side of the second equation. Here, the number of electrons are matched. So I'm going to cancel both electrons and we're going to add both the reactions. So in first reaction, the pending part is iron, which is in solid state, plus 2 times of H plus, which is an aqueous medium, gives Fe2 plus, which is an aqueous medium, plus hydrogen gas. So this is the overall cell reaction. Here Fe was oxidized to Fe2 plus and H plus gained electron, which means H plus reduced to get converted into hydrogen gas. So basically this overall cell reaction is a redox reaction. Fine. So could you please tell me how many electrons were involved in this whole process?
2 electrons.
Very good. It has to be 2. You should not tell it is 4. And Madhavan was right. Here it is 2 electrons because here 2 electron was lost by iron and that same electron was gained by H plus. So total electrons involved is just 2 electrons. So the value of N is 2. Fine. So I'm going to substitute the values here. E cell, which is equal to E naught cell, minus 0.0591 divided by 2 log. What are all the products here? In overall cell reaction, what are all the products?
Fe2 plus and H2.
Yes. So Fe2 plus an aqueous medium. So there will be concentration. And as far as hydrogen is concerned, it is gas. For a gas, then concentration term is not applicable. It is pressure, right? So pressure of hydrogen divided by here. What are all the reactants?
Fe and 2H.
Okay, and here iron is in solid state. Last class we have discussed for any solid or for pure liquid, the concentration will be 1. So a concentration of iron, which is in solid state, got a concentration as unity. So it is going to be 1. And what is the next species? I've written the concentration of iron is 1. I'm not going to write that. Next, the concentration of H plus ion. See here, we have number of ions in the. We have number of ions for H plus, so we have to write the number of moles in the power. Okay, that's it. So now we have to calculate the E naught cell. And what is the formula to calculate E naught cell?
E naught cathode minus E naught anode.
Right. I'm going to give you the potential values. First of all, you have to check whether this is oxidation or reduction potential. Is it oxidation or reduction potential? From this representation, we can identify whether
From
this is oxidation.
reduction potential.
Very good. So we can use these values. Could you please tell me the value of E naught cell?
Minus 0.44.
Minus 0.44. Which is anode and which is cathode? Which is cathode?
Sorry, ma'am, plus 0.44.
So electrode potential of cathode is 0 because cathode is hydrogen. Reduction potential of hydrogen is 0 minus reduction potential of anode is minus 0.44. So E naught cell is plus 0.44. That's it. So 0.44 minus 0.0591 divided by 2 log concentration of Fe2 plus was? What is the concentration of Fe2 plus? It isn't the problem.
And 0.001 mole.
Yes. So which can be written as 10 power minus 3, right? So it is 10 power minus 3, and pressure of hydrogen gas is 1 bar divided by concentration of H plus ion is 1 molarity. Here it is whole square. Now you have to simplify this. 0.44 minus this can be written as 0.0 2 0.02
95.
0.0295. Okay. And simplify those log values. So this is log 10 power minus 3. So it is like log a power b. So log a power b can be written as, you have to bring this power to the front. So it is b log a. So it is 0.44 minus 0.0295 into minus 3 log 10. What is the value of log 10? What is the value of log 10? Last class we have discussed the log values also.
1.
Very good one. So substitute the value of log 10 and simplify and let me know the value of E cell. At least tell me the approximate value.
From 0.43117.
0.43, not exactly, Kanna. See, 0.44 minus into minus, it is going to be plus. If you round off this value, it is 0.03, right? So you have to multiply these two values and you have to add with 0.44. So it is
0.44983, ma'am.
No. See, if you multiply these two values, it is 0.09.
0.52.
That's it. 0. 0. You're right. Your answer was right. Approximately 0.53 volt.
53.
That's it. So could you please tell me whether this reaction is a spontaneous reaction or non-spontaneous reaction? Whether this reaction is... Come again? Is it spontaneous or non-spontaneous reaction?
Spontaneous.
Very good, it is spontaneous reaction because the sign of E cell is positive. So it is spontaneous reaction. And from this E cell value, we can also calculate the value of delta G. And what is the formula? Delta G is equal to minus N.
Minus NF E.
E dot.
Kanna, see, if you have delta G in the left side, then the formula will be minus NF E cell. Okay. And if it is delta G naught, then the formula is minus NF E naught cell. Okay, here uh, I'm going to use the value E cell. So the formula will be delta G is equal to minus NF E cell, right? We know the value of N, which is number of electrons involved, 2 here. That's it. Farad value is 90,500 coulomb. So we have all the values, so we can find the value of delta G also. But here they didn't ask for that value, but I'm just telling from the value of E cell, we can also calculate delta G. And here is the activity, Kanna. Here I've given two more cells, right? For which you have to write the Nernst equation and also you have to find the EMF, which is the E cell. Okay, and I'm going to give you the data. What is SN?
Scandium.
SC is scandium. It is tin. So these are all the values you need to calculate the E naught cell. Okay. Could you solve this problem? Is it possible for you guys to do it as activity? Okay. So shall we move on to next concept then? Okay, Kanna, fine. So we'll discuss the next concept. Listen here. I'm going to write a hypothetical cell reaction. A moles of A is reacting with B moles of B to give C moles of C and D moles of D. Okay, and number of electrons involved is En. Is it possible for us to write the Nernst equation? All the chemical species were in aqueous medium. Could you please tell me the Nernst equation? What is the formula? E cell is equal to
E naught cathode minus E naught anode.
Kanna. That is for E naught cell. I'm asking for E cell. So the formula is E naught cell,
Not cell
minus
0.059 by N log product
concentration
by
of product by reactant. According to this equation, what are all the products here? C and D were products, right? A and B were reactants. So concentration of the product. So here C is the one of the products. So concentration of product. Here we have to write the number of moles on the power. So C power C and
D power D.
D power D. And in denominator,
A power A, B power B.
that's it. If suppose, if the system is at equilibrium, then is it possible for us to write the equilibrium constant? You have studied in your 11th standard. What is the equilibrium constant representation? Kc is equal to concentration of products by reactants. And also last class we have discussed if the system is at equilibrium, then what will be the value of E cell? E cell will be 0. E naught cell will never be 0. Okay, when the reaction is at equilibrium, E cell will be 0. So if the system is at equilibrium, we have E cell value as 0 and we have Kc. So I'm going to substitute these two terms in Nernst equation. So what is the expression? Left side we'll be having 0 E naught cell minus 0.0591 divided by n log. We can replace this complete term by, we can replace this complete term by,
KC.
that's it, Kc. When system is at equilibrium, Kc is equal to concentration of product divided by reactant. So since the system is at equilibrium, I'm going to replace this term with Kc. So I'm going to bring this E naught cell to the left. So we'll be having minus E naught cell. So minus minus will get cancelled out. So what will be the final formula? E naught cell is equal to 0.0591 divided by n log Kc. So this is the relationship between equilibrium constant and E naught cell. Okay, that's it. As Nernst equation, this equation is also a very important one. So we have to know the formula of Nernst equation for electrode, for cell, and this formula as well. Okay, we may expect questions from these Nernst equation part. Fine. And one more relationship, this you have studied in your thermodynamics. Delta G is equal to delta G naught plus RT ln K. At equilibrium, as I've told you here, at equilibrium, E cell is 0, right? Similarly, at equilibrium, delta G will be 0. So could you please rearrange this equation? If delta G is 0, then
Del G naught plus RT lambda is equal to 0.
Kanna, left side it will be 0, right? 0 is equal to delta G naught plus RT ln K. Now I want this delta G naught to be on the left. So
Delta G naught is equal to RT lambda.
is that so?
Minus RT.
If I'm bringing this delta G naught to the left, it will be then minus delta G naught, which is equal to RT ln K. And throughout, I'm going to multiply it with negative. So delta G naught is equal to minus RT ln K. Now I want ln to be log. So I have to convert ln to log. We know the values of log and not for ln, and there is a way to convert a natural logarithm ln to log. Ln is equal to 2.303 log. So the final formula is delta G naught is equal to minus 2.303 RT log K. That's it. Could you please tell me what is this K represents? What does this capital K represents? Of course, it is equilibrium constant because here we are talking about equilibrium reaction, right? So this K is nothing but your equilibrium constant. It can be a Kc or Kp, but it is the equilibrium constant. You're getting my point? Any doubt, Kana? Fine. That's it. So shall we move on to next concept?
Yes, ma'am.
Okay. Now we're going to see few fundamental parameters which you have studied in your physics also. Resistance. Resistance can be represented with the alphabet capital R, and it is directly proportional to L and it is inversely proportional to A. Right? What is this L and what is this A represents?
L is length, A is area.
Okay. So you're in your physics, you would have studied, like, if this is your wire, this is the length of the wire and this is the area of cross section of the wire. But here we are not talking about metallic conductance. So here we are not talking about metals. Here we are talking about electrolytic conductance. So here we have electrolytic solution in which I'm going to have two electrodes. Basically, there are two metals. These are the metal surfaces. So distance between the two electrodes is L and area of the electrode is A. Okay. So here it is the distance between the two electrodes and A is the area of the electrode. Yes. So it is resistance is directly proportional to L and it is inversely proportional to A. I'm going to replace this proportionality symbol with a constant rho into L by A. So what is this rho? R is resistance, L is the distance between the electrodes, A is the area of the electrode, and rho is nothing but
Density.
See, that is the rho is the general representation of density, no doubt about it. But here, this rho represents not the density but specific resistance. Specific resistance. What is the another term for specific resistance? You have studied in your physics. Resistivity. Resistivity. Okay, fine. Now we'll come up with the units for all these parameters. What is the unit of R? What is the unit of R? What is the unit of resistance? It is very easy.
Ohms.
Very good, Om. Or we can use this symbol also. What is the unit of distance or the length? It should be in?
Meters.
Very good, it is in meter. What is the unit of A? It is the area. So, meter square. And what is the unit of resistivity? So, to find the unit of resistivity, I'm going to rearrange this formula. I'm going to find the value of rho, which is equal to R into A divided by L. So, what is the unit of R? Which is ohm, right? And what is the unit of A, which is meter square? What is the unit of L? It is meter. Then I'm going to cancel these two meters. Now, what is the unit of resistivity? What is the unit of resistivity?
Ohm meter.
That's it, ohm meter. Fine. So we are done with resistance and resistivity. Now we're going to check for conductance. I'm going to represent conductance with the alphabet G and not C. It is G. So what is conductance? It is the reciprocal of resistance, right? And what is R, Kana? We know what is R. Could you please tell me what is R?
Rho L by A.
Yes. So 1 divided by rho into L by A. So I'm going to bring the area term to the numerator because area and denominator is denominator. So G is equal to 1 by rho into L and I'm going to bring this area to the numerator. So G is equal to 1 by rho into A by L. Kanna, rho is the constant. So reciprocal of constant is going to be another constant, right? So G is equal to the new constant I'm going to represent with a symbol kappa. It is not K. It is called kappa. And this kappa represents specific conductance. Or what is the another term for specific conductance? The another term for specific resistance is resistivity. So similarly, what is the another term for specific conductance?
Conductivity.
That's it, conductivity. So G is equal to kappa into A by L, or what is kappa? G into L by A. This is the very, very famous formula, very important also. So specific conductance is equal to conductance into L by A. Here L by A is called as cell constant. That's it. So now we'll write the units of all the parameters. What is the unit of conductance? Unit of conductance. Conductance is 1 by resistance. So what will be the unit then?
Ohm inverse.
Very good. Ohm inverse. Or it can be mho. Or it can be ohm inverse, or it can be Simon. We can use any of these units. Okay, it is for conductance. And how about conductivity? Conductivity. Conductivity is equal to conductance into L by A. What is the unit of conductance? It is Simon into what is the unit of length? It is meter. Unit of area is meter squared. So 1 meter and 1 meter
Ohm
will get
inverse,
cancelled.
meter inverse.
Very good, Kana. So kappa's unit is Simon meter inverse. So Simon can be replaced with ohm inverse or mho. Anything is fine. Okay, that's it. Could you please tell me the unit of cell constant then? Unit of cell
Meter
constant.
inverse.
That's it, meter
Meter
inverse.
inverse.
Very good, Kanna. It is meter inverse. Okay. So we may expect question from these formulas also. Okay, which is very easy. You can expect very direct question. Okay. I'm going to give you a problem. Kanna, it is the very direct problem, so I want you to solve it. I'm going to read out this question. The resistance of a conductivity cell containing 0.001 molar potassium chloride solution at 298 Kelvin is 1500 ohm. What is the cell constant? If conductivity of 0.001 molar potassium chloride solution at 298 Kelvin is 0.146 into 10 power minus 3 Simon centimeter inverse. See, this prefix may vary. It can be meter inverse or centimeter inverse or picometer inverse. Anything is fine. It is just the unit of cell constant. That's it. So they're asking for the cell constant. So as we know the relationship between cell constant, conductivity, and conductance and all that, please use the relationship and find the value of cell constant. What is the formula? Or what is the relationship between cell constant and conductivity? See, here we have resistance. They're asking for cell constant and we have conductivity. What is the formula, Kanna?
Kappa is equal to conductance into L by A.
That's it. So kappa is equal to G into L by A. We have to calculate L by A. So I'm going to have this L by A one side and I'm going to bring the rest of the parameters to the other side. So kappa into 1 by G, which is equal to L by A. So you have all the values. Please substitute the values carefully and tell me the value of cell constant.
Thousand 500 copper.
Mm-hmm. Kana, what is kappa? Kappa represents conductivity, right? What is the value of conductivity?
0.001 mole.
Aha, that is the concentration. Conductivity of this potassium chloride solution at 298 Kelvin is 0.146 into 10 power minus 3 Simon centimeter inverse. So, what is the value of kappa? Kana, what is the value of kappa? Bhumika, what is the value of kappa? It isn't the problem.
0.01, ma'am.
0 point? No, Kana, it is not 0.001. See, the unit is 0.001 molarity. So, it is the concentration. You just read the sentence. Conductivity of 0.001 molar KCl solution at 298 Kelvin is 0.146 into 10 power minus 3 Simon centimeter inverse. So I'm just asking the value of kappa.
0.146 into 10 to the power minus 3.
That's it, Rakshan is right. So kappa is conductivity. Conductivity is this one. See, from the unit itself, we can identify, right? So 0.146 into 10 power minus 3 Simon centimeter inverse. So we have kappa. Here, the formula we have G, but here we are provided with resistance. So, what is the relationship between resistance and the conductance? We know R is equal to, or G is equal to 1 by R, or R is equal to 1 by G, right? So, here we are provided with the resistance value, which is R, or it is 1 by G, right? Which is 1500 ohm. So we have the value of kappa and also we have the value of 1 by G as well. Please substitute in the formula and come up with the value of cell constant. I want it with the unit. Can I substitute and simplify and come up with the unit? And also the value. See, kappa is nothing but 0.146 into 10 power minus 3 Simon centimeter inverse into 1 by G is 1500 ohm, which is equal to L by A. Here, Simon
200
is. Mm,
219.3 into 10 to the power minus 3.
right. Right, Kana, you're right. What is the unit? So Simon can be written as ohm inverse. That ohm inverse and ohm will get cancelled out. So L by A is equal to. So he told me in terms of 10 power minus 3, I'm going to simplify it 0.219 centimeter inverse. That's it. So shall we move on to next concept?
Yes, ma'am.
Okay. Fine. Now we're going to learn a new term which is called molar conductivity. I'm going to represent with a symbol this one. What is this? What symbol is this?
Ma'am, can you show me the before slide, ma'am? Thanks, ma'am.
What is this symbol, Kana? Lambda. This symbol is lambda, and actually, this is capital lambda. Okay. So it is nothing but I'm going to have an electrolytic solution. Okay. Basically, I'm going to dissolve electrolyte in water and whose concentration is 1 molarity. So in this electrolytic solution, we'll be having lot of ions, right? So these ions are responsible for the conductance inside the solution, right? So conductivity of this 1 molar electrolytic solution is called molar conductivity, and the formula to calculate molar conductivity is kappa divided by concentration. Okay. And here they are talking about molarity. Concentration can be, or formula can be this one, kappa divided by molarity. Okay. So this is the general formula. But in books, the formula will be kappa into 1000 divided by m. So now we'll see how this formula changes to kappa into 1000. Fine. But the general formula to calculate molar conductivity is kappa divided by molarity, kappa divided by concentration of the solution. But in books, the formula will be kappa into 1000 divided by molarity, or in some places you'd have you'll be seeing it as kappa into 10 power minus 3 divided by molarity. So we have to know how this 1000 or 10 power minus 3 is coming to the formula and when we have to use those formulas. Okay. So first of all, we have to know the unit of all these parameters. What is the unit of molarity? What is the unit of molarity? What is the formula of molarity? Number of moles of solute divided by volume of the solution in liters. So unit of number of mole is mole, and unit of this volume of the solution is liter. So liter I'm going to bring to the numerator. So it is mole per liter. So molarity is unit is mole per liter, and we know the unit of kappa. What is the unit of kappa? Simon.
M to the power minus 1.
Simon meter inverse, or Simon centimeter inverse. Anything is right. Okay. Now we know we know the unit of kappa, we know the unit of molarity also. From these units, we have to find the unit of molar conductivity. So lambda m is equal to unit of kappa is let us use this formula. Let us use this unit, Simon centimeter inverse divided by mole per liter, right? I'm just going to bring this per liter to the numerator. So lambda m is equal to Simon centimeter inverse mole into liter. See, here we have no common terms to cancel, but we know the relationship between liter and centimeter. See, 1 liter is equal to 1 decimeter cube. There is no conversion at all. For 1 liter and centimeter cube, it is 10 power 3 centimeter cube, and 1 liter is equal to 10 power minus 3 meter cube. So, this is the relationship between liter, decimeter cube, centimeter cube, and meter cube. Here, since we have centimeter inverse, I'm going to write liter in terms of centimeter. So, what is 1 liter in terms of centimeter? 1 liter is equal to,
1000.
very good, very good. So it is 10 power 3 centimeter cube divided by mole. It is 1000 or 10 power 3, both are right. So 1 centimeter inverse and 1 centimeter will get cancelled out, so the unit will be 10 power 3 Simon centimeter square per mole. So what I'm going to do is I'm going to use this unit and 10 power 3 in the main formula. So what is the final formula? Lambda m is equal to kappa divided by molarity into 10 power 3, which is 1000, and the formula, the unit is Simon centimeter square per mole. That's it. So in your question, if the value of kappa is given in terms of centimeter, then you please use this formula. If the unit of kappa is given as Simon centimeter inverse, then please use this formula. Okay. Or if suppose if kappa is given in terms of Simon meter inverse, then we can derive the formula for that also. Lambda m is equal to kappa divided by molarity, and now the unit of kappa is Simon meter inverse and the unit of molarity is mole per liter. I'm going to bring the liter to the numerator. What is the relationship between liter and meter? Liter and meter?
10 power minus 3 meter cube.
Very good. So 10 power minus 3 meter cube divided by per mole. So lambda m is equal to 10, 10 power minus 3 Simon meter square per mole. Right, that's it. So in your problem, if kappa is given in terms of Simon meter inverse, then please use this formula. Lambda m is equal to kappa divided by molarity, and now it is 10 power minus 3 Simon meter square per mole. Okay, so you have to be very careful with the unit of kappa. If the unit of kappa is 10 power centimeter Simon centimeter inverse, use the first formula. If the unit of kappa is Simon meter inverse, then please use the second formula. Okay, am I clear? You're getting my point?
Yes, ma'am.
Fine. I'm going to give you a problem. Please solve and come up with the value. So it is a very direct problem. The conductivity of 0.2 molar solution of potassium chloride at 298 Kelvin is 0.0248 Simon centimeter inverse. Calculate its molar conductivity. Do you want any clue? It is a very direct problem. They're asking for molar conductivity, and we are provided the values of conductivity and concentration. You just substitute, but the thing is, you have to choose the correct formula for that.
1.24.
Yes, 1.24.
Yes, pm power square mole inverse.
Is it just 1.24, Madhavan?
1.2400.
There is no 10 power term.
Multiply it, ma'am.
Okay, but that is not the exact value, Madhavan.
0.0124 into 10 square.
Okay, fine. See, you have some 10 power terms, right? Could you please repeat your value?
0.0124 into 10 square.
10 power 2. And what is the value? 0.0?
124.
Mm-hmm. Okay. See, how about rest of the students? Madhavan got this value, but I want some other student to please check or check at your end. Bhumika, what is the value, Kana? What is the molar conductivity?
124, ma'am.
Okay, it is 124 for Bhumika. And Rakshan, what is the value? And what is the value for Aditi? See, you told me two values. One is 0.0124 into 10 power 2, and Bhumika's answer is 124. And among these two values, one answer is right. So, how about Aditi and Rakshan? See, the answer is 124 Simon centimeter squared per mole. This is the exact answer. And Madhavan, can you please check at your end? This is not the value, Kana. What
Okay, ma'am.
formula you used? What formula you applied for this problem?
First formula.
In terms of 10 power 3, right?
Yes,
See,
ma'am.
lambda m is equal to kappa is 0.0248 into 10 power 3 divided by concentration is 0.2, right?
Yes, ma'am.
So you have to cancel these two values, right, Karna?
Okay, ma'am.
So this is the answer, 124 Simon centimeter squared per mole, right? So we are done with molar conductivity. Now we know what is molar conductivity, right? So if we have 1 molar electrolytic solution, the conductivity of this 1 molar concentrated solution is molar conductivity. Now we're going to check for the factors which influences this molar conductivity. Okay, so the topic is factors influencing molar conductivity. Okay, so the first factor is nature of electrolyte. What is electrolyte, first of all? What is electrolyte?
Anode and cathode.
That is electrode. Electrodes are anode and cathode, but electrolyte is, it can be,
Solution.
okay. Actually, it is any chemical compound. If you dissolve this any chemical compound into water, that chemical compound will get dissociated into cations and anions. Then that chemical compound is called an electrolyte. Or if you take any chemical compound and you melt it, the molten form will have cations and anions. So that is called an electrolyte. The classic example is your sodium chloride, which is in solid state. And if you dissolve sodium chloride in water, it will be Na plus and Cl minus. So if it is Na plus, see, all the ions will be in aqueous medium. So it is the compound which get dissociated into cations and anions inside this aqueous medium. So this chemical compound is called as an electrolyte. Okay. For example, HCl. If you dissolve HCl into water, how it will get dissociated?
H plus Cl minus.
So HCl is an electrolyte, right? Okay. So electrolyte is the substance which dissociate into cations and anions inside the aqueous medium or in its molten form. Fine. So we know what is electrolyte. But we have two types of electrolytes. See, as far as sodium chloride and HCls are concerned, if you dissolve or if you add 100 molecules of sodium chloride inside this aqueous medium or inside water, all the 100 molecules will get dissociated into Na plus and Cl minus. Now tell me how many Na plus and how many Cl minus will be there if you dissolve 100 molecules of NaCl? If you dissolve 100 molecules of NaCl or if you add 100 molecules of NaCl, how many Na plus and how many Cl minus we can expect inside the solution?
50 Na plus 50 Cl minus.
See, I'm going to dissolve only one NaCl and one NaCl will give one Na plus and one Cl minus, right? If you dissolve 10 NaCl, then you can expect how many Na plus and how many Cl minus?
10 Na plus.
10 Na plus and 10 Cl minus. Similarly, if you add 100 NaCl, you can expect 100 Na plus and 100 Cl minus. So all the sodium chloride was dissociated into cations and anions. Okay. So this kind of electrolyte is called strong electrolyte. But there are some other electrolytes. Again, the classic example is this one. Could you please name this compound? CH3COH.
Acetic acid.
Very good. If you dissolve this acetic acid inside a water, it will get dissociated into CH3COO minus, which is an anion, and H plus, which is a cation. And this is not the complete dissociation, it is the partial dissociation, which means If you add 100 molecule of acetic acid, only few molecules will get dissociated. For example, if 20 molecules was dissociated, then we can expect 20 CH3CO minus and 20 H plus, and we'll be having 80 undissociated acetic acid. So this also giving cations and anions inside the solution. So this is also an electrolyte, but here there is no complete dissociation. It is just the partial dissociation, and this kind of electrolyte is called weak electrolyte. So now we know what is electrolyte, and we know the difference between strong and weak electrolyte, right? Now I have two beakers. In first beaker I have strong electrolyte of 1 molar concentration. Here I have weak electrolyte of 1 molar concentration. Though the concentrations of the solutions were same, number of ions produced will be equal or not. Though the concentration of the both the solutions are same, I want you to tell whether both the solutions will have same molar conductivity. What is molar conductivity? Conductivity of 1 molar electrolytic solution, right? So, for example, I'm going to give you a hypothetical value. Here, I'm going to dissolve 100 molecules of strong electrolyte. All the 100 molecules will give 100 cation and 100 anion. So, totally, we have 200 ions here. As far as a weak electrolyte is concerned, I'm going to add 100 molecules of weak electrolyte here. But since it is a weaker one, maybe 30 electrolytes was dissociated. So because of which we have 30 cations and 30 anions. So totally we have only 60 ions, right? So though the concentration of the solutions were same, the ions produced were completely different, right? And these are only these ions are responsible for the conductivity, right? So though the concentrations are same, the ions produced were different. Now tell me, among strong and weak electrolytic solution, which will have the higher molar conductivity? Among these two solutions, which will have the higher molar conductivity, whether it is strong or weak electrolyte? Though the quantity of electrolyte we added inside the solution was same, the ions produced were not equal, right? In strong electrolyte, the number of ions produced was greater than the ions produced by weaker one. So now tell me, which will have greater molar conductivity?
Strong one.
That's it. So nature of electrolyte matters a lot. Strong electrolyte will have the higher molar conductivity. So though the concentrations are same, strong electrolyte will have greater molar conductivity. That's it. Fine. Now we'll move on to another parameter, which is viscosity. Hannah, could you please tell me what is viscosity? The viscosity term represents how thick the solution is. Okay. If the solution is very thick, then that is highly viscous liquid. If the solution is very thin, then that is least viscous or less viscous liquid. For example, I'm going to have one beaker of water, another beaker of honey. Could you please tell me which is highly viscous? Is it water or honey?
Honey.
That's it. So I'm going to have two beakers. In both the beakers, I'm going to add NaCl, or I'm going to add a strong electrolyte. I'm going to have strong electrolyte in both the systems of same concentration. But here the solution is less viscous and this is more viscous. In both the solution, the number of ions produced will be same. But who's responsible for this conductivity? the ions and its mobility, right? These ions produced by electrolytes are responsible for the conductivity, and if the ions are free to move, then we'll have more conductivity. If the ions can't move properly, then their molar conductivity will get reduced. Okay, because basically the conductance or conductivity is the flow of charged particle. Here, the charged particle we are talking about is the ions. So if the ions are free to move, then their molar conductivity will be more. If couldn't move, then molar conductivity will be less. So in both the solutions, I have strong electrolyte of equal concentration. So the number of ions produced in both the beakers will be same. But could you please judge the conductivity of both the solution? I mean, conductivity of or mobility of ions in both the solution. The ions present in first beaker will have different molar conductivity than the ions present in the second beaker. Am I right? In which beaker ions are free to move? Can I visualize and tell me? In first beaker, I have less viscous liquid. In second beaker, I have more viscous liquid. And in both the beakers, I have same number of ions. And generally, ions are capable of moving. And now I want you to tell in which beaker ions are free to move. Is it in less viscous or in more viscous liquid?
Less viscous.
Less viscous liquid, very good, Madhavan. So, in less viscous liquid, ions are free to move. So, that kind of solution will have greater molar conductivity. So, if conductivity is, I mean, if the viscosity is less, then molar conductivity is higher, right? So, are they directly proportional or inversely proportional? They are inversely proportional. Okay, fine. Next is size of the ion. Kana, now tell me how this molar conductivity depends on the size of the ion. Kana, I want you to tell me how this molar conductivity or the ion's mobility depends on the size of the ion. I'm not expecting any perfect answer. I want your perspective. That's it. See, how these ions will. I mean, if the size of the ion is less, then its mobility will be more, right? That is what our expectation is, right, Kana? If the size is lesser, then they are free to move. So what we'll be expecting is if the size of the ion is less, then they are free to move, then molar conductivity will be greater, right? So our expectation is smaller ions will have greater molar conductivity. That is what our expectation is, but actually it is not happening. For example, I have beaker full of water. Okay. And the shape of water is bent. And each water molecule will have this sharp separation as we know. And inside this inside this aqueous medium, we are adding sodium chloride, and we know Na plus and Cl minus will be dissociated. Since this Na plus is a positively charged ion, it will attract the negatively charged species, right? And here the negatively charged species in water is oxygen. So oxygen will get attracted towards Na plus. So could you please name the system you have studied? See, this is called solvent cage. Na plus is attracting the solvent molecule because of electrostatic force of attraction. So this Na plus is positively charged species, so it will attract the negatively charged oxygen. So negative charge of, so negatively charged oxygen, which is from water. So this Na plus will be surrounded by a lot of water molecule. So this is like a cage, and this cage is built by the solvent molecule. So that is called solvent cage. It will be like a spear, or it will be like a cage, and inside which Na plus was trapped. And similarly, Cl minus also, since it is negatively charged one, it will attract the positively charged H plus. So this also will have the solvent cage. Okay, now we'll understand the size of the solvent cage. Generally, this is a cation. This is also a cation. So this cation will also attract water molecule. This cation will also attract water molecule. But among these two cations, which cation will attract more water molecule? The attraction of water molecule is because of its positive charge, right? So among these two ions, this B2 plus got more positive charge, so this will attract more water molecule. So size of the solvent cage will be greater here than this one, right? Size of the solvent cage will be greater. So if the positive charge on the cation is more, then the size of the solvent cage will be more. So this kind of ions cannot move easily because ions will be moving along with the solvent cage. Here the size of the solvent cage is huge. And also among this A plus and B2 plus, this B2 plus got lesser size. Though the actual size of this cation is lesser, the size of the solvent cage is huge, so it cannot move properly. So according to this solvent cage perspective, you have to understand that size of the ion is directly proportional to the ionic mobility, and it is directly proportional to the molar conductivity. Because if the size of the ion is greater, then the solvent cage around this ion will be lesser, so the ions can freely move, due to which molar conductivity is getting increased. Okay, so size of the ion is directly proportional to molar conductivity. That's it. So we have two more parameters. One is temperature, and another one is concentration. So concentration, we're going to discuss it in next class. But temperature is very easy. Could you please tell me, if the temperature of the solution is high, then how will be its molar conductivity, or how will be the mobility of ion? The temperature is high, then they are free to move. So temperature is directly proportional to molar conductivity. As simple as that. Okay. And next class we'll be discussing the concentration part, which is very important, from which we'll be discussing Kohl-Roschla and all that. So today, what are all the stuffs we have discussed, Kana? We have discussed the problems related to Nernst equation, and also we have discussed conductance, conductivity, resistance, resistivity, cell constant, and problem related to that. And we have discussed molar conductivity, unit of molar conductivity, and the problem related to molar conductivity, and finally factors influencing lambda m. That's it. So I've given a couple of problems for activity also. Please solve the problem and share it in the group, or please come up with answer in the next class. Okay? Fine. Do you have any doubt? If so, please ask me, or we'll wind up the session. Then shall we wind up the session, Kanna? Madhavan, Rakshan, Bhumika, do you have any doubt?
Yes, madam.
Fine, Kanna. Okay, sir. Okay. Thank you, sir.